Today is going to start a series of 2 lectures that focus on developing mechanisms from information that we have. And sometimes that information takes the form of experimental data, and sometimes that information will take the form of just known things. And so in the first example that we're going to solve, we kind of have a little bit of both. So we're looking at this irreversible reaction of toluene and hydrogen to give benzene and methane. And so that reaction is given right here. And I actually prefer to write it so I don't have to carry complex chemical formulas around, right? I just want to simplify it if I can. So I'm going to look at this as T plus H2 gives us B plus M, right? Or toluene plus hydrogen goes to benzene plus methane. Now for this reaction, it's known that hydrogen and methane do not strongly adsorb onto the surface. So this is going to be a little bit of a change for what we did in previous lectures. And then what we're asked to do is to use the experimental data to the left to determine the rate limiting step and to calculate the value of the reaction rate constant and the pertinent equilibrium constants that we're going to come across in solving this problem. So the first thing that I want to do when I look at this is just write the overall reaction, right? We have T plus hydrogen gives us benzene plus methane. And if we were to start to look at this in a very similar way to how we talked about these complex mechanisms, we need to start writing steps, right? Now we know that these two, right, are not on the surface, but we do know that benzene and toluene will be. So the first step in our reaction mechanism, if we try to conceive one, should be the adsorption of toluene, because we know it has to be on the surface in order to react. And so we can have reaction 1 be, toluene plus an active site gives us an adsorbed toluene, right? And we'll just call that forward reaction rate constant equal to K1. Now we need to react the adsorbed toluene to give us adsorbed benzene. And from the stoichiometry we have in the overall reaction, well, we know that this then has to react with hydrogen. And we would have written this in equilibrium. And we would then have written adsorbed benzene, plus we know that methane is not adsorbed on the surface, right? And we would say that this has some reaction rate constant K2, right? And that's reaction 2. And then the last step in this mechanism could just be the desorption of B, right? So we have benzene goes to, or the adsorbed benzene goes to desorbed benzene plus a site. And if we wanted to think about this as an overall reaction, right? That site is going to cancel, the adsorbed toluene is going to cancel, the adsorbed benzene is going to cancel, and here we get T plus H2 gives us B plus M. Now, an interesting thing here is that this reaction and this are not exactly the same, because the mechanism that we're supposed to look at is irreversible. But the thing that we've written here is completely reversible. And so one of the things that we haven't talked about yet is that when you have an irreversible reaction, typically it is the rate determining step that is irreversible. It's not always true, but it is mostly true. And so if that's the case, then the very first thing that we must do before we get this mechanism correct, and then to determine the rate law, is we have to figure out which of these steps is the rate determining step. Now, how are we going to do that? Well, in our previous class, we showed that we could do this by looking at the shape of initial rate plots. And remember that when we had something that looked like minus RA0 versus CA0, when it was a straight line, that was adsorption controlled, right? Or the adsorption step was the rate determining step. When we had a line that initially was semi-linear and then had an asymptote that was surface reaction limited. And finally, when we had a horizontal line, that was desorption controlled. So when I see the data set that we have been given, to me, the most logical thing to do then is to find a way to plot the negative of the initial rate divided by the initial of the concentration. Now, if we look back at the data set, we don't have the data explicitly in terms of concentration. We have it in terms of pressure. But don't forget that the concentration, let's say, of toluene at the beginning is just the pressure of toluene at the beginning divided by RT. And so plotting the pressure data is the exact same thing as plotting the concentration data. Okay, and that's something to remember. We've talked about it a few times during the course of the semester. And so one of the things then that we can do is, if we know that we want to look at the effect of just the toluene, well, we can take a look at the experimental data that we have that doesn't have some of these product species in it, that only has hydrogen and only has toluene at the beginning, because we're looking for what's happening when there isn't any product, right? And that's something that we did in our previous class as well. So if we want to look at the data set here, I just put it in Excel. And if we look at where there's essentially no products, but there are both reactants present, well, in set D, that is this data set right here, where the pressure, the initial pressure of toluene is changing, the pressure of hydrogen is held constant, although it doesn't adsorb on the surface anyway, and the initial concentrations of methane and benzene are 0. And so one of the things then that we could simply do is plot the data in column C here against the data that is in column D. And if we do that, here's what we see. So we have a plot that starts to increase. We could call it semi-linearly. There aren't that many data points there. And then it levels off to give us an asymptote. And then, so if you remember that from our discussion a minute ago and the lecture last time, this means that the surface reaction is going to be the rate determining step. And so if we go back to our mechanism, that actually means that reaction 2 is the rate determining step. And so what we can do then is draw this not as an equilibrium, because we know it's an irreversible reaction, but we know that that's the rate determining step, and that the rate determining step here is going to be irreversible. So this is our mechanism, right? We have toluene plus hydrogen gives us benzene plus methane. We have an adsorption step, we have a surface reaction, we have a desorption, and it takes everything into consideration that we know, right? So we don't have hydrogen or methane that's adsorbed, and from the data we have, right, we deconvoluted the surface reaction as the rate determining step. So that's great. And if you look at the problem statement that we've been asked to do, one is to propose a mechanism. The second one is to determine the reaction rate constant from the data and the equilibrium constants that are required. Now, of course, if we're talking about rate constants, well, we will have a reaction rate constant, and then we're also going to have K1, and I guess we'll call this KB since it's the desorption of B, okay? And here, Ka, sorry. Actually, A doesn't make any sense there, does it? There you go, we'll call that KT. So let's do this. Let's figure out how now we're going to use our experimental data to determine the rate constants. But we don't know which ones we need here at the beginning. So from the mechanism, we need to find our rate law. And since the second step here is the rate determining step, that we know that RT is equal to minus K2 times the concentration of toluene on the surface times the pressure of hydrogen, right? And so if we look at this, obviously the pressure of hydrogen we can measure. And so we need to figure out how we can determine the concentration of toluene on the surface here. And of course, we're going to use the fact that at all of the non-rate determining steps, that the rate of the reaction divided by the rate constant is approximately equal to 0, right? For the non-rate determining step. And so let's do this for reaction 1. And so we know that reaction 1 over K1 is then equal to minus, oh, sorry, we already have K1. So it's equal to minus the pressure of toluene times the number of vacant sites plus K1 over KT of the concentration of T on the surface. And that's equal to 0. And so now we can easily solve for this, right? CT dot S is just equal to, and sorry about this, right? That K1 shouldn't be there, right? That should just be KT times the pressure of toluene times the number of vacant sites. And so we have RT prime then just equals minus K2 times the pressure of hydrogen times the pressure of toluene times KT times CV, right? So now what we need to find in our mechanism, just like we did in lecture 18, was CV, and we do that through our site balance. And so we know that the total number of sites equals the number of vacant sites plus the number of sites that are occupied by the adsorbed species. And here that's toluene and benzene. And we already have an expression for this. And so now we need to develop an expression for that. And to do it, we're going to use the other reaction, right? So we know that R3 over K3 is also approximately equal to 0. And that's just equal to CB dot S minus the pressure of B times the number of vacant sites divided by KB, right? Or simply that CB dot S equals PB times CV over KB. And so if we finish this site balance, the total number of sites equals CV plus KT, oops, that's a little big, KT times PT times CV plus PB CV over KB, or that it's just CV times 1 plus KT times PT plus PB over KB. And finally, right, then CV just equals CT divided by 1 plus KT times PT plus PB over KB. And if we plug this into our rate law, right, we get that the rate of T prime, right, equals minus K2 times KT times the pressure of hydrogen times the pressure of toluene times the total number of sites divided by 1 plus KT times PT plus PB over KB, okay? And the other way that we could also think about this is that all of these things that are constant, right? The, K2 times the equilibrium constant for toluene times the total number of sites, we're just going to call that the equilibrium constant K. And we find a simplified version of this, right? RT prime equals minus K times the pressure of hydrogen times the pressure of toluene over 1 plus KT PT plus PB over KB. And there's our rate law using the information that we have. So we have a rate law. And now what we need to do is find the values for the relevant equilibrium constants and the rate constant. So essentially what we need to do is use the experimental data to find K, to find KT, and also to find KB. Okay. So before we do that, I just want to open this up to you guys so you can ask a question or any questions that you have about what we've done so far or how it relates to what we did last time.
What was the advantage of changing K2KT to just K? Are we going to be able to find that more easily through the experimental data?
Yeah, so we will not be able to independently find these three things. And so often what's done instead, especially because this is a constant, this is going to be constant, is to lump them into one parameter. And then these constants just end up being buried in the equilibrium constant. Because remember, like K will still equal K0 times the exponent of minus EA over RT. And the activation energy here will be the activation energy of the rate determining step. And then these things that are constant they'll just be buried inside of that K0. Good question. Yeah,
Thank you.
Yeah, very good question. All right, anybody else have a question they want to ask? Okay, so how do we do this? How do we actually determine these parameters? Well, there's actually two ways to do this, okay? The first one is we'll call it, a step-by-step analysis. And it might be even better called an estimation. But we're trying to be quantitative here, so I don't often love to call it an estimation. So we'll just say that we're going to go step by step, okay? The second way to do this is a multivariate analysis. Okay, so we're going to do both of these today. One of them, believe it or not, is considerably shorter than the other one, and that's 2. And that has been enabled by, the fact that, computers are insanely powerful now, and they can solve this problem in, fractions of a second after we set it up properly. But we're going to do this sort of old school first, and then we'll do the multivariate analysis. Okay, and a lot of times, the old school methods relied on plotting and relied on us being able to make reasonable simplifications to data, and then to plot them, and then to extract parameters from that data. So let's do that. And so in the step-by-step analysis, the first thing that we're going to take advantage of is the fact that we know that if it's a surface limited reaction, right, that the initial rate here plotted against the initial pressure, right, goes up and flattens out. And the value here where it flattens out is essentially going to be equal to, if we look at our data here, where, if you remember in this rate law, when there is no B present, which we use to make this plot, right, this term actually goes to 0. And then as the initial pressure of toluene increases, the 1 doesn't really matter anymore. And so what's left then is that the pressure of toluene goes away, and that, we're essentially left in this problem with something that's like the reaction rate constant times the pressure of hydrogen. Okay, and so if we want to look at it that way, then let's just find the asymptote using our experimental data. Okay, and so earlier we plotted all those data points where where the initial concentration of the products was equal to 0. And so now what we need to do is to estimate the value of the asymptote here. And actually the data set, if you look at it, is still increasing here. So my eye initially wanted to say, oh, look, it's about 135, right? But it's still not quite flat, but the slope is changing. And so upon further review, I thought, well, maybe it'll flatten out up there somewhere. And so my estimate looking at this graph is not, about 135. It was about 140. And so we're going to say that K is then equal to 1.40, and the units were times 10 to the minus 8 moles per gram times atmosphere seconds, okay? And actually the unit here didn't have atmospheres in it. The reason that we get that is because this is equal to 1.4 times 10 to the minus 8 moles per gram seconds. And then if we divide by the pressure of hydrogen, and if we look at all of the data that we considered previously, the concentration is 1 atmosphere. And so we end up dividing that by 1 atmosphere. And that's where atmospheres comes in the rate constant. And so just from the value of the asymptote here, right, we have a rate constant, right? 1.4 times 10 to the minus 8 moles per gram atmosphere seconds, okay? So that's the first parameter. Now all we need to find is KT, and we need to find KB as well, all right? So let's do that. And let's, essentially do the exact same thing or use the same set of data that we used here, and think a little bit about how we could transform our rate law to then extract that parameter, all right? So our rate law is here, right? That we have RT prime is equal to minus K times P hydrogen, P toluene over 1 plus KT, PT plus KB, or PB over KB. So I'm going to start this by taking the inverse of this expression, okay? And if I do that, I get 1 over RT prime equals 1 plus KT PT plus PB over K3 divided by the numerator, which was K times the pressure of hydrogen times the pressure of toluene. And I'm going to multiply both sides of this equation by the denominator on the right-hand side. And so we get K times the pressure of hydrogen times the pressure of toluene over the rate equals 1 plus KT times PT plus PB over K3. And the nice thing about this is that we're using the cases in that previous data set where PB was equal to 0, right? And so essentially what we did in the data set was we went from the full data set to, we can go to a subset of the entire data set where PB is equal to 0. And we should be able to use that data then to determine KT. And here's how we're going to do that. We're just going to plot K times P hydrogen times P toluene over the rate versus the pressure of toluene. And if we do that, the slope of that curve should be equal to KT. All right. So I did that, and we get a very, very nice straight line. And that's all of the data points. And you can see in Excel, essentially what we can do is calculate that value, okay? And then plot it. So there's the plot, and I just use the trend line. And we can see then that the slope is basically 1.00. And so KT from the slope is equal to 1.00. Okay. So there's the first equilibrium constant and the rate law using the experimental data. Now, what about KB? Is it possible for us to use the same approach and find KB? And the answer is yes. So I'm going to borrow this expression already, right? I'm just going to paste that down here. And now if we want to find KB, what are we going to do? Well, we're going to use the cases where PB is not equal to 0. In the data set. And so that means that we're going to take again, right, a subset of the data here, not the full data, but all of the cases where PB is not equal to 0. And you can see there's only 5 of them. There are only 5 experiments that were done. And our sheet becomes pretty simplified here, right, with these 5 data sets. Now, what are we going to plot? That's a good question. So my suggestion here is to take K times the pressure of hydrogen toluene over RT prime, right? These are all measurable things or things we've already calculated, minus 1 minus KT times PT, right? And that's just equal PB over K3. And now what we can do here is we can just plot this versus the pressure of B. And the slope of that line equals 1 over K, and sorry, KB, not K3, right? 1 over KB. And I did that as well. And so we find that the slope is equal to 1.26. And so if we look at KB, that just equals 1 divided by 1.26, which is equal to 0.79. And so now what we've been able to do is use subsets of the experimental data to estimate the reaction rate constant, to estimate the equilibrium constant for the adsorption of toluene, and to determine the equilibrium constant for the adsorption of benzene. Okay. All right. So do you guys have questions about the second step where, after we determine the rate law, we then determine the reaction rate constant, we determine KT and KB? Okay. So if that's the case, let's do the second method, which actually is reasonably straightforward. So we're going to do our multivariate analysis here. Okay. Now, if we're going to do that, I guess the question is exactly how? Well, we know from the experimental data here that we've measured the rate. And we know that the reaction rate is given by our rate law. All right, so let's borrow this again. Okay, even make it a little bit bigger. Okay, so we have our rate law here. And we have a couple of things in the rate law that are unknown, right? So the first thing that's unknown was this rate constant. So let's replace that, right? So we didn't know what that was. We didn't know KT, and we didn't know KB. And so what we're going to do in a multivariate analysis is that we have the experimental data that gives us the real reaction rate. So what we want to do is to find values for K, KT, and KB that minimize the error, right? For all of the data, like the entire data set that we're talking about here, okay? And so one of the things that we're gonna do then is guess initial values for K, KT, and KB. And we're gonna use the ones that we calculated in our estimation, right? Or when we did the step-by-step here. So we said that the reaction rate constant was equal to 1.40 times 10 to the minus 8. We said that K1 was 1.0, or sorry, KT was 1.0, and KB was equal to 0.79, okay? So let's see if those are correct using our multivariate analysis. So here's what I did. Set up an Excel spreadsheet where I first inserted these values for the equilibrium constant. That's multiplied by a factor, but that doesn't matter here, times K1, and there's KB. Then what I did was I set up 3 columns, where one was the calculated rate using the rate law. And so I did that for every single data point here, where I calculated the reaction rate. Now from the data, we know exactly what the reaction rate is. So I calculated a difference between the values that were estimated from our guesses here and the actual reaction rate that was measured. And then when you're trying to minimize error, the square of the difference is actually a much better indicator of what the error is. And the thing that you're trying to do to get the real parameters is to minimize the sum of squares. So I have a cell here at the bottom, which is just the sum of all of these differences squared, okay? And so to find the value here, right, we just have to minimize the sum of squares. And I'm gonna do that using the solver function in Excel. And our target cell is the sum of squares, right? So we're gonna take J22, and we're gonna minimize that value. Now, oftentimes when we do these problems, we're interested in the actual value, right? That we're trying to solve a system of equations. But here we just want to find the minimum value by changing these 3 parameters. And in this case, I know that all the values have to be positive. So I'm going to leave this box checked to make the unconstrained variables non-negative. And I'm going to click solve. And through a multivariable analysis, we can see what the real values are for K, K1, and KB. And we can see that our calculated values from plotting and from estimating the asymptote were pretty close. They weren't perfect, but they were certainly usable. And so we find that the actual value for the rate constant was 1.44 times 10 to the minus 8, not 1.4. K1 is 1.04, not 1.00. And KB is 0.72, not 0.79. So now that we have these values, we can solve real problems. So one of the things that we could do if we wanted is that we could solve a problem that's based on a packed bed reactor. And we know that the rate law for a packed bed reactor, DFT, or maybe let's start with the general form, right? DFI dW equals Ri prime, right? And the prime just indicates that that the rate constant is per mass of the catalyst. Well, we know dFi dW, right, then would equal, dFT dW would be equal to RT prime. And we have this, right? We know that RT prime is K times the pressure of hydrogen times the pressure of toluene over 1 plus K1 PT plus KB, or PB over KB, sorry. Right? And we could solve this problem. And in our textbook, they do this. This is actually example 10-2. You guys will also get some practice with that example problem on the homework. And that's a very interesting problem where they also take pressure drop into consideration inside the reactant. So you guys will do one version where you don't take pressure drop into consideration, and another one where you do. So that'll be in homework 5. The other thing that we could do, other than just solving the problem the way that it is that we could look at some other interesting things. Like we could ask questions about the ratio of benzene and toluene on the surface as a function of the conversion. This might be something that we're interested in. And we don't even have to solve this full problem for us to do that. And that's also something to keep in mind as we solve problems, is that it's not always needed to do the most complicated thing first. And so let's look at this, right? Let's look at the ratio of toluene and benzene. So let's just take, CTS over CBS. Well, we solve for these, right? We know what the concentration of toluene is on the surface, right? We know that's just going to be equal to K1 times PT times CV, right? We came up with that relationship at the beginning of our lecture today. And we know that CB dot S is just the pressure of benzene times CV over KB. And so the CVs are going to cancel with each other. And we know then that this is just equal to, right, KT times KB times PT over PB. And we actually know, if the temperature is constant and the pressure and the total pressure is constant, that in this particular reaction, it's like A plus B goes to C plus D. So delta N is equal to 0. And if that's the case, remember that, CA0 or CA would just equal CA0 times 1 minus the conversion. In this case, right, we could make that simplification, which also means that the pressure of toluene just equals the initial pressure times 1 minus the conversion. And since we're forming B, right, if we were to write this in terms of concentration, we would know that CB would just be equal to CA0 times X. And in this case, this is actually the pressure then of B, of benzene, equals the pressure of the initial pressure of toluene times the conversion. And so we actually could put this into our expression. And we know CTS over CB dot S is then equal to KT times KB times the CA0s will cancel. That's just 1 minus X over X. And remember, we just found this using the experimental data. So we could, without even doing any complicated Euler's method in Excel, we could find some things like what would the surface adsorption or the ratio of the surface species be as a function of the conversion. It could be something that we want to know. And so here's that ratio. And the left-hand plot just shows from, conversion very close to 0 to 1. And then the plot here on the right-hand side is just zoomed in a little bit to go from 0 to 10 instead of 0 to 80. So you can see really where the action is. And so at the very beginning of the process, there's a bunch of toluene on the surface. And then towards the end, right, as the conversion goes to 1, there's none, because we've actually transformed all of the toluene then into benzene, right? And then the benzene's also going to desorb. So you may not be interested in that ratio specifically, but it's just an example of some things that are buried in the derivation that we did and buried in the data that you could find interesting.